Okay, so good morning. So looks like everybody has submitted their first homework. So good news, thank you, and yeah, hope we'll have a very good semester together. So today we're going to continue looking at the induced flow near the aircraft and look at what is the effect. How can we learn from the induced flow near the aircraft about the effect of taper, sweep, and twist of the wing planform? Okay, so first of all, let's actually make sure we all get the problem we did last lecture. So just to remind you, last lecture we were looking at the flow closer to the airplane, and we were thinking about the flow described by actually one infinitely long vortex that loops through the wing of the airplane, right? So there are three legs of this infinitely long vortex. Two legs are the trailing vortices that goes from the wingtips back to infinity downstream of the airplane. And the third leg actually goes right through the wing. That's the bound, that's called the bound vortex. Now, in order to calculate the flow field anywhere, it's good to consider the effect of all three parts of the vortex. And we started, what is the effect of we first studied what is the effect of a very small segment of the vortex, right? And that is described by the Biot-Savart law. And the direction of the flow is always quite intuitive. You can just put your thumb in the direction of the vortex, right? And the direction of the flow induced is always going in the direction of your other four fingers using a right-hand rule. So that's the direction. And the magnitude of the flow induced by just a tiny segment decays like 1 over distance squared. So instead of decaying like 1 over distance, like an infinitely long vortex, a small vortex has the effect decaying like 1 over distance squared. But then we perform the integral of that infinitesimal segment, right? And figured out this equation, which describes the induced flow of a vortex of either finite or semi-infinite or infinite length. Okay, so, and today we're going to use this example to illustrate what these two angles are. So here, in this formula, just a reminder, gamma is the circulation of that vortex, okay, over 4 pi x, and x is the direction, is the distance between the observation point, okay, and the nearest point on the infinite extension of that vortex line. So it's kind of the orthogonal distance to that vortex. And we'll also use examples to illustrate what x means. And theta L and theta R are the angles between that orthogonal direction. So this is the orthogonal direction and the line that connects the end of the vortex to the observation point. Yes, you have a question?
Yeah, so like if the point is on the other side at the same distance, like refracted, is it going to be the same answer or be minus?
Very good question. If the point is on the other side of the vortex, are we going to get the same answer or it's reflected? So remember, like we have been talking about a vortex that has the circulation, right, in that direction, right? So if we're looking at this point, there are multiple ways to look at it, but like the easiest way is to actually just look at the problem in the opposite direction. Just think about, like, put your eye behind the whiteboard, right? And if you look at this image from behind the whiteboard, it'll look exactly the same as this one. So the velocity you get, if you get a velocity into the board for this one, you're going to get a velocity, if you think about viewing from the other side, out of the board, right, for this point. So yes, it'll be reflected, because if you use a right-hand rule, it'll be going in here and going out here, right? Okay, good question. Any other questions I can clarify before I go into these examples? Okay, so now going to the examples, let's consider the first point. So everything for 1, 2, and 3 are in the xy plane, right? So both the observation points and all the vortices are in the xy plane, which means z equal to 0. So let's just draw question 1 in the xy plane. So x would be x is this way, y is that way, right? And in the xy plane, the airplane looks like that. So we have a vortex that on the right, on the right wingtip is going that way. On the left wingtip is going that way, and across the wing is going that way, right? Okay, and the first point is over here, very, very far downstream. So first of all, let's just look at our formula again. So gamma is the strength of these vortices. There is nothing we can argue about that. And what is x? X for the two trailing vortices are both half b, right? That's the distance between the observation point and the nearest point on the infinite extension of these two vortices. So it's half b here, half b here. And to the bound vortex, the distance is infinity, right? Okay, so that automatically makes the effect of the bound vortex 0, because I'm dividing by infinity for the bound vortex. So we don't have to consider the bound vortex at all. And when we're considering these two vortices, as we did in the last semester, right, we have the two angles, one being 90 degrees, one being minus 90 degrees. So as a result of that, the difference between these sine angles would be 2. And that 2 cancels with this 4 pi x to get us 2 pi x. So we get the same formula as the infinitely long vortex, which here it is essentially infinitely long vortex, right? Because from the point of view of point 1, this vortex extends infinitely backwards and pretty much infinitely forward also. So the effect is okay. And you also use the right-hand side rule to get the sign of the velocity. So the effect of this vortex, the flow goes down. The effect of this vortex, flow also goes down, right? So by combining these, what I get is gamma over 2 pi b over 2 and double, so times 2. So what I get would be 2 gamma over pi, right? And it goes downward. So that's the answer to the first question. All right, any questions on that? That's kind of the easiest one. No? Okay, so let's go to our second one. Our second one, the vortex never changes, right? The vortex is the same, but we're looking at this point. And the distance to all the 3 legs of this vortex are half b. And if you look at the direction of the induced flow, from the 2 trailing vortices, they are still going downward, right? And for this vortex, it's also going downward. So 3 downward velocities added together. But the magnitude is now going to be different. Okay, so the magnitude is going to be gamma over 4 pi half b. And let's look at the bound vortex first. For the bound vortex, we have the angle between, okay, so just remember again, like the angles are angle between the observation point connecting with the end of the vortex and the direction, right, of x, where the direction of x is the direction between the nearest point on the vortex and the observation point. So what we essentially get is we are going to be getting a sine of 45 degrees minus sine of minus 45 degrees. Right? Okay. And the result is going to be, of course, the difference is going to be square root of 2. So what we get is gamma 2 pi b times the square root of 2. So that's from the bound vortex. Okay, any questions? Okay, these two angles, you can think about this angle being minus infinity if it extends all the way downward, right? It goes to minus 45 degrees here, to 0 here, to 45 degrees here, and to 90 degrees when it goes infinitely above. So these are how the angles work. Okay, and from the two trailing vortices, it's very similar for pi b over 2, except for its sine of 45 degrees, right? Again, like we have this 45 degree angle, actually not this angle anymore, because it's now the x direction is this, right? And the angle would be actually, yeah, would be this angle. So 45 degrees minus sine of minus 90 degrees. So that would be a little bit different. So it'll be 2 pi b gamma 1 plus square root of 2 over 2, right? So that's from each trailing vortex. All right, does it make sense? So again, like when I'm looking at the angles, right, it'll be minus 90 degrees if the end is all the way here, right? It'll be minus 45 degrees here, and actually let me look at if I'm right. It'll be minus 45 degrees here, 0 here, 45 degrees here, and 90 degrees over here. So I think instead of writing it like this way, I should actually write it differently. So it should be actually 1 minus sine of minus 45 degrees, right? That's more consistent to the picture we're drawing here, right? Because the two ends, it's 90 degrees over here, minus 45 degrees over here, right? Yes?
Wait, so it's sine theta L minus...
Yeah, it's...
Sine, wait, so like what's the left and what's the right?
Okay, so 1 means this end, right? So remember, like yesterday we were looking at the picture where the vortex points upwards, right? So 1 would be the upward end of this vortex, in this case 90 degrees, and minus the downward end of the vortex, which in this case is minus 45 degrees.
So how does the left and right play into it then? Because you just said something on the right minus something on the left, in reference to the point when looking at the vortex.
Sorry, can I ask you a question again?
Yeah, if you go down to the observation point,
yeah,
you're looking straight at the vortex.
Yeah.
You have the right side here and the left side here.
Yeah, yeah.
I thought we did the left side minus the right side. We were doing the right side minus the left side.
Yeah, so what we were doing was if you orient this to the picture we looked at yesterday, which is basically rotating this by counterclockwise by 90 degrees, right? We were looking at the x-axis pointing from the vortex to the observation point, and y-axis going in the positive direction of the vortex. That was the coordinate system we used on Monday.
So could you denote theta L and theta R in your example?
Can I denote? Okay, so for this vortex, right? Theta. Did I use L and R? What did I use? So basically, maybe let me denote this. Let me see. What did I use? Yeah, L and R, right? So in this case, I think the L and R would be opposite. So this would be theta R, theta L, and the angle between this and this would be minus theta R. Right? So theta L would be almost 90 degrees. Theta R would be minus 45 degrees. Yes?
Yeah, why did it flip? Yeah. Because, like, I guess I don't know if I'm the only one having this problem, but it's like I can't really differentiate when we use the left and the right for this type of example. It's like,
yeah, so basically the theta comes from a change of coordinates. Let me think what is the best way to think about it. So theta comes from a change of coordinates because we are integrating in the direction of the vortex, right? And the theta comes from a change of coordinates in the sense that the x times tangent theta would be equal to the location we're integrating in this vortex. Okay, so if theta equal to 0, right, x times tangent theta would be equal to 0, so I'm integrating exactly here. If theta is equal to a positive number, my x times tangent theta would be positive, right? So I would be integrating over here. So if theta is 90 degrees, that means I'm integrating all the way to infinity in that side.
no, I agree with that. It's just the order of what you're doing the subtraction. I guess it's like the part that's throwing me off.
Yeah, the order I'm doing the subtraction is remember, like the original integration, right? The order is always from the plus y side, right, minus the bigger y side minus the smaller y side, right? So y is the coordinate along the vortex direction. So I'm always going to be having the bigger y, right, minus the smaller y. And in this case, the bigger y corresponding to a bigger theta, the smaller y corresponds to a smaller theta. Okay. So, right, so essentially, like, when you're looking at a point that's kind of at the nearest distance to the observation point, this is y equal to 0. So this is basically theta equal to 0, right? And when you go from that point towards, like, along the direction of that vortex, we have an increasing theta. And if you go in the opposite direction, we have a decreasing theta. Okay, and the subtraction is going to be from the bigger theta minus the smaller theta. And then you figure out the direction of the velocity using the right-hand side rule. Okay, is that clear? Yes?
So why is it on the top one that theta r is in the greater y, and we subtract theta l minus theta r for that?
For which one, sorry?
Like the one in blue on top, we did theta l minus theta r, but that would be that lower y value.
Oh, yeah, so, sorry, we did theta L minus theta R because I think the other day we said the velocity is in the minus z direction, right? So this would actually calculate the velocity in the z direction, not just the magnitude. If you do theta R minus theta L, that'll give you the magnitude of the velocity with a positive number, and you figure out the sign by the right-hand side rule. Yes, that's a good point. I didn't mention that. So this formula, I think we derived strictly from the Biot-Savart law with the and this actually is the is the velocity in the z direction, right? So the sign of this actually tells you it's in the negative z direction. So theta L is always smaller than theta R, right? So this subtraction always would give you a negative number in the coordinate we were looking at among them. And here, if you do sine theta R minus theta L, flip the direction, you're always going to get a positive number. And you can use the right-hand rule to get the direction. Yes. What is your question?
I kind of don't have my question.
Okay. All right. Yes?
My question is, like, I guess where intuitively does the L and the R come from? It means left and right, right?
Mm-hmm.
So, like, is that the way we should think of it, or should we think of it as, like, large theta and small theta?
Yeah, let's just think about it as as the larger theta in the positive direction of the vortex minus the smaller theta in the other direction. Maybe put it as theta plus, theta minus might be easier, right? So maybe put this as theta minus and theta plus. Maybe that's easier to think about. All right. Does that help? Okay. So maybe I should give maybe it'll be clearer if I give example number 3, because example number 3 actually involves some other angles, right? So here, like, all the angles are it'll involve angles that are different from this example. Okay, so number 3, right, near upstream. So here the vortex goes like this, and this. The vortex is still the same, but now we're looking at this point, number 3. Okay, so first of all, the induced flow from the bound vortex. Now when you look at it, right, so this is the example, like you have mentioned. The point is on the left, so it is easier to look from behind the whiteboard, right? So if you look behind the whiteboard, we have an angle over here. So this is the plus theta, right? It's plus 45 degrees. This is the minus theta, is minus 45 degrees. Anything below would be even less than minus 45. Anything above would be even more than plus 45. And this would be 0, right? So this is the magnitude of the velocity. To calculate it, you would have sine of plus 45 degrees minus sine of minus 45 degrees. Okay, so the induced flow from the bound vortex would be gamma over 4 pi half b sine of, just write it down, sine of 45 minus sine of minus 45. Now from the trailing vortex, it's now different. Intuitively, the effect of this trailing vortex should be more or less than if the trailing vortex extends not from here but all the way from here, as in the previous case. Should be less, right? Because it is the effect of this part of the vortex should be the effect of this part minus this part that is no longer here, right? So the effect of this vortex to this point should be less than a vortex that extends all the way from here to here, which, if you shift the coordinates, is actually exactly the effect of the same vortex to the point number 2, right? So that is saying the effect of the trailing vortex to point 3 should be less than the effect of the same vortex to point 2. Okay, now let's look at it numerically. What is the distance x? The distance x now here is the distance from the observation point to the infinite extension of that vortex. So the distance here is again b over 2. All right. So although the vortex actually ends over here, but when you are calculating the x coordinate, you are still calculating the x coordinate assuming that this vortex lies on the y-axis. So the x coordinate is still b over 2. So we have gamma 4 pi b over 2. And now what are the angles? Okay, so if we think again like in plus and minus angles, what is the plus angle that corresponds to the most positive side of that vortex? 90 degrees. Any other answers? Correct, 90 degrees, right? It extends all the way to here. That's the most positive coordinate you can think of. All right? Okay, again, we said that's 90 degrees. This would be 0, and this would be negative. So what is this angle? Is it positive or negative? It's positive, right? Because that's 90 degrees. This is 0. This is between 0 and 90 degrees. And what's the value? 45. That's right. All right. Okay. So between these would be between 0 and 45. Beyond that would be between 45 and 90 degrees. Okay. So here I have sine of 90 degrees minus sine of 45 degrees plus 45 degrees. Remember, in the previous example, it's sine of 90 degrees minus sine of minus 45 degrees, which was greater than 1, and in this case, it's less than 1, right? So that's the primary difference, and the result you get is of 2 pi b 1 minus the square root of 2 over 2. All right. Yes.
Why is this one minus sine of positive 45 as opposed to minus sine of negative 45?
That is because in this example, this endpoint corresponds to a positive angle. In the previous example, we were looking at a point like here, which corresponds to a negative angle, right? And remember, yeah, so this would be 0 angle. The point the closest to the observation would be 0 angle. Anything towards the positive side is positive angle, towards the negative side is negative angle. I mean, this angle is obtained through the change of variable, really. It is like this coordinate starting from here, right, is equal to the x times sine of that angle, right? So that's that's the origin of that angle, where it comes from. All right. Okay, any other questions that can help illustrate how you should do calculations? Make sure it's clear, because you get a homework assignment that requires you to do this either tonight or tomorrow morning. All right. So if you have questions, ask now. Okay, if now let's actually look at the point 4 and point 5. That actually requires you to do some three-dimensional thinking now. You have a question?
So we did this for one of them.
Oh, yeah. So we did this for one trailing vortex, right? And the other trailing vortex, yeah, you can use symmetry to say the effect is the same. Or we can repeat the calculation again. The other trailing vortex, let's say the port side, this is the starboard side. We have, again, the distance is distance to here, right? It's still half b. And so it's 4 pi half b. And now my y-axis aligns in this direction, right? So what is the theta plus? Again, this point would be 0, right? This point closest to the observation would be 0. And the vortex is in this direction. So the most positive side is this, right? What is going to be the angle here? 45, but is the sign positive or negative? Remember, here is 0, right? And the positive direction is this for the vortex. It's negative, right? Okay, again, why is it negative? Because the closest point is going to be 0, right? By definition of that change of variable. And the positive direction always is the direction of the vortex. All right, so this is negative 45 degrees. How about the other end, the negative end? What's the angle here? It's the minus 90, because that's the most negative you can think of, right? That extends to infinity. So that example, we have sine of minus 45 degrees minus sine of minus 90 degrees. And so the result is going to be exactly the same. It's minus square root of 2 over 2 minus 1, which again is 1 minus this. Right, so these two velocities are the same, and they both point in which direction? Into the board or out of the board? They all point into the board. How about the bound vortex? is the induced flow from the bound vortex into the board or out of the board? Out of the board, right? And which one is larger? Let me just do this calculation. This is equal to 2 pi b gamma times a whole square root of 2, right? So if you add these two up, is it bigger or smaller than this? I mean, square root of 2 is like 1.4-ish, right? 1 minus square root of 2 over 2 is like 0.3-ish. So add them up is 0.6-ish. This by itself is like 1.4, right? So this is actually a lot bigger than the sum of these. As a result, the velocity points this way or that way? Out, right? Out is the positive z direction. Okay, so ahead of the airplane, the velocity goes upward. That's exactly what we saw on the wind tunnel test. Yes?
Sorry, I just have one question and clarifying in like just the order on the port side of the angles and like which one you should subtract. You said to kind of think about it in that like the first one is like the negative theta. Is it that which one is like more negative in the situation where we have like two negative numbers?
Yes.
Because you were saying like the 45 degrees is more.
To figure out the magnitude of the velocity, right, you always do the bigger number, subtract the smaller number. The bigger sine of the bigger angle, subtract the sine of the smaller angle, right? And the bigger or smaller is always which one is in the positive direction aligned with the vortex. Just pick this angle, whichever is more positive according to the angle. That number is going to be subtracted by the smaller number to get you the magnitude.
The angle in which the direction of the vortex is like pointing.
Yes. Because that determines like the sign of the angle, right? Anything that's more positive, that's go along the direction of the vortex, and past the nearest point is going to be positive angles. Not yet past the positive. The closest encounter, that's the negative angle. All right. Okay, good. Okay. All right. So now let's look at just the one of these points either above or below. So maybe look at the one above, number 4, right? Okay. So for number 4, the bound vortex has a distance equal to, again, half b, right? If you look at the coordinate, x, y coordinate are both 0, so they are the same coordinate as the bound vortex, right? And the distance is exactly the z coordinate, half b. Okay, and from the point of view of the bound vortex, number 4.4 is basically a 90-degree rotated version of 0.3, right? So the induced velocity is going to have exactly the same magnitude of this one, but the direction is what? Yes, the direction is going, right, 0.4 lies like closer to you from the board. So if my thumb points towards the direction of the vortex, right, the velocity goes downstream. So the same magnitude I'm just going to copy here in the x direction, in plus x direction. Okay, but the trailing vortex, again, I'm going to do one by one. Let's just do this trailing vortex. What is x? What is the distance between the trailing vortex and the 0.4? It's no longer b over 2, right? It's offset by b over 2 in the y direction, but also offset by b over 2 in the z direction. So the distance is going to be square root of 2 over 2 times b, right? Okay. And how about the angles? Again, like it's this point, the angle of that infinite point minus the angle of this point. The angle of the infinite point now should be pretty clear. What is it? 90 degrees, right? Okay, how about the angle of this point? Remember that this is the closest point, right, on that vortex to this, so it is 0, right? Okay, so I have sine of 90 degrees minus sine of 0, so that's, of course, 1, right? So the effect is gamma over 4 pi this guy square root of 2 over 2b times 1, right? That's sine 90 minus sine 0. Let me just write it down clearly. Sine 90 minus sine 0. All right. And what's more importantly, what direction does it point towards?
Like 45 degrees.
Yes, 45 degrees. Both down and into the, like both downwards and into the board, right? It's kind of 45 degrees, so you have to use your right hand side rule. Imagine this point 4 is over here, not exactly on the board, so the velocity goes like skewed like that. Okay, and similarly, if you do towards this vortex, you're gonna see that the higher angle is going to be 0, the lower angle is going to be minus 90 degrees. Again, if you do subtraction, it's equal to 1, right? So the magnitude is exactly the same, but the velocity is going to be pointed into the board, which is the same as this one, but also upwards. So the up and down component from these two vortices cancel, and the into the board component, the minus z component, do not cancel. So if you add, so basically we are not supposed to multiply this by 2, but instead multiply this by square root of 2 to get the combination of these two, velocity vectors that are like 90 degrees in angle, right? Okay? Yes?
Could you potentially illustrate that?
Yes. So to illustrate that, I think what is the best way? So the best way is to look at the YZ coordinate. Okay, in YZ coordinate, I have two vortices. The starboard vortex goes towards me. The port side, the vortex goes into the board, right? Let me see, X, Y, Z. Yeah, okay. So we are looking at point number 4, which is here. And from this vortex, this vortex goes towards you, right? So let me actually use a different color. So this color is this guy. For this vortex, the velocity goes like that, and for this vortex, which goes into the board, the velocity goes like that. So the combination of that is, so this is a square, right? The combination of that is square root of 2 times the strength of each one of these velocities. All right. Are we good? Okay. Yeah, so point 5, you can do it similarly. All right. Okay. Yeah, so I don't think we have time to do much more. So, but like I'm just going to illustrate a 6th point. So how about if we have a 6th point at the center of the wing? So number 6 here. Okay. What is going to be induced the velocity at the 6 points? So the reason I'm bringing this up is that there is actually a fallacy of modeling the flow field using this kind of what we call concentrated, like ideal vortices. The fallacy is that the velocity is going to be infinite with an undefined direction if you look at the induced velocity exactly on top of a vortex. Okay, so this is a fallacy of modeling the flow field in these kind of ideal vortices, because if you look at a real flow field, there are no vortices that are represented with a kind of a mathematically ideal line which has zero thickness, right? All the vortices actually has a core, we call like a vortex core, of finite diameter. But this kind of a model assumes all the vortices have zero diameter. Like, that's why the velocity becomes singular when you approach these vortices. So to avoid this kind of a fallacy, we usually say that, okay, if you're picking a point right through a vortex, just ignore the induced velocity from that vortex, right? Because if you consider a vortex actually of finite core or of finite diameter, at the center of that vortex or finite diameter, that vortex actually has no effect. All right. So this is why I'm just introducing this point. So if you look at the induced velocity at here, you should only look at these two trailing vortices. All right. And what is the effect? Maybe let's just do very quickly this calculation. So the distance, of course, is half b and also half b, right? And the angles are, well, if you look at this vortex, right, on the positive side is 90 degrees, negative side 0 degrees, right? So 1 minus 0. On this part, the vortex points towards this direction, so 0, theta equal to 0, theta equal to minus 90. So again, it's 0 minus minus 1 is equal to 1. So the strength of the induced flow, of course, is going downward, and you can use right-hand side rule to do this. So from each vortex, pi over 4 pi, b over 2, it's either sine of 90 minus 0 or sine of 0 minus sine of minus 90, in which each case it is equal to 1, and then multiplied by 2 because there are two vortices. So this is going to be the flow at point number 6. All right? Questions? Okay, so I'm bringing this up because in your homework you have to be able to deal with the flow, induced flow. Some of them are on a vortex. So maybe I'm just going to do a little bit more. Let me see. What should I spend the remaining time on? Okay, so first of all, maybe just quickly answer these questions, right? How do the induced velocities in all of these cases scale with gamma and the span of the wing? Yeah?
Linearly with gamma, inversely.
Yes, linearly with gamma, proportional to gamma, like all the velocity has a gamma on top, right? And has a b on the bottom. So yes, they scale proportionally to gamma, inversely proportional to the span of the wing. Okay? And then, how do the induced velocity scale with the flight speed, total lift, and the span of the wing? Basically, if you look at these variables, right, the span of the wing is the same as the span of the wing, but now gamma is gone. So question 3 is essentially asking you to, how do I represent gamma as a function of the flight speed and the total lift? Oh, and also air density rho, right? Well, that's using our conservation of momentum stuff, right? Okay, remember, like gamma, going back to our like far wake analysis, gamma, its circulation is equal to the integrated velocity around a circle, right? It's velocity times length. And we also did calculations saying, okay, if we have a pair of vortices of strength gamma, the flow speed integrated on the infinitely long vertical line, right, goes up and down to infinity, is actually exactly equal to gamma if that line lies in between these two tip vortices, right? Do you remember that analysis? So if I have a pair of vortices, if I integrate the velocity along that line, the integral is exactly equal to gamma. Okay? So if we perform a two-dimensional integral of the total momentum over a volume of finite depth, so let's say if I have a depth of v, which is the flight speed, right, times delta t. Basically, that's this direction over the airplane traveled in this direction for this much depth, right, over a time of delta t. Then I would get a total momentum of air in the vertical direction, in downward direction, being, first of all, well, let me just say, okay, so integration over the x direction, dx, and over the depth, right? So this is x directional depth, v delta t. So this is how long I'm integrating the x direction. And the y direction is this. So I'm integrating over the span, right? Because outside of this, I get a 0 and 0 dy, and the integration in the z direction, dz, times how much momentum per volume I have. What is momentum per volume? Momentum is mass times velocity. Momentum per volume is mass times velocity by volume, which is rho, right, times velocity. Okay? And integration over dz of velocity. I mean, I can just pull rho out of this thing. Integration of v dz is exactly what we have calculated, right? So that's basically we are integrating, these two integrals are integral over constants. So I can just do v delta t, the x extent, times b, the y extent, times the z integral, which is gamma. So that's how much momentum of air I get in time of delta t. If I divide this by delta t, my lift is going to be this number divided by delta t, which is rho v b gamma, right? Okay, so that means my gamma is equal to my lift divided by rho vb. All right. And the induced velocity, let me call W, the induced velocity, it is proportional to gamma over B, which is equal to L over rho VB squared. Okay, so this is basically the scaling of induced velocity, actually in pretty much all scenarios. If I have higher lift, I get a higher induced velocity. If I get a higher density or higher flight speed or higher span, I get a smaller induced velocity, right? Like remember, we saw this accident of an airplane flying into a wake of a helicopter, right? That's exactly the scenario where lift is high. Well, air density we have no control, but like if the helicopter is flying at higher altitude, the airplane is going to be suffering even more, okay? And slow velocity for a helicopter and the small span, that's also what a helicopter does. So that's, yes.
I understand like the math, but intuitively, like if you're moving faster through the air, you'd be obstructing more air, right? So why doesn't that work for this?
Good question. So intuitively, if you fly faster, why don't you create more velocities? Well, your intuition is actually going to be correct if we are not looking at the velocity downward. Okay, if you are thinking about a velocity forward, so if you stand by like a moving train, right? After the train passes by, you feel a wash of air. That's not going up or down. That's actually going in the direction of the train. So that's actually something we'll study later on the viscous effect. So the viscous effect, which creates drag, actually brings air in the same direction as the traveling airplane. That is actually going to scale proportional to the forward speed of the airplane. But here we are talking about induced flow. That's lift-induced flow, right? That's in the orthogonal direction as the travel. So if you fly faster, higher V, that means you are pushing more air in the orthogonal direction, right, per unit time. And because of conservation of momentum, if you can push more air, then you don't have to push it as hard as if you're pushing less air. It's actually the same as like a rocket equations, right? I mean, if you look at a rocket, you have the choice of either having the exhaust in a very high speed, right? In which case you are pushing the air very hard. So to get the same thrust, you need less propellant, right? So so in this case, it's very similar. So if you have a higher velocity, it's almost like you have more propellant to push against. Therefore, to get the same force, you need to push it less as hard. So that's the intuition behind why higher velocity means a lower induced speed. All right. Any other questions? I guess we'll have to do the effect of a taper next week. All right. Okay, so see you.